Hi everyone, today I would like to discuss about two very important concepts in estimation, namely maximum likelihood and maximum posteriori estimation. So in the last video I discussed about Bayesian versus frequentist estimation. I gave you what Bayesian approach is, what frequency approach is, what's the cons and pros of using each one. Further, I introduce you to the concept of a likelihood function and also posterior distribution. If you have not already seen this video, I will give you a link in the description to check out that video. It definitely helps you to understand this video better. But I will review the concept needed to understand the ML and map estimation. Now, the goal of this video is to tell you what is the objective or goal behind the ML and map, and also tell you how to formulate your problem or how to solve the problem involving the ML or map estimation. Okay, so let's start. So I will start from the ML, maximum likelihood. ML or maximum likelihood. Great. First of all, what does it mean? I will write goal or slash objective, goal slash objective. During the maximum likelihood, we are trying to find the parameter theta. Find the parameter theta. Or I have to say that maybe trying to estimate. They're a very generic concept. Find maximum likelihood perhaps is the most widely used estimation technique used in machine learning, statistics, digital communication, and signal processing. So we are trying to find or estimate the parameter theta in such a way that the likelihood function is maximized. Likelihood function is maximized. Great. So what is a likelihood function? I explained about that in my video, Bayesian versus frequentist approach, or Bayesian versus frequentist estimation. But definitely check out that video. The likelihood function is usually denoted by L of theta x, where x is a data and theta is a parameter. It's defined as the probability of observing data, x1, x2, all the way to xn. So here, let's say use one variable, only x, given the parameter. So it's the probability of observing the data given the parameter. This is what they call it the likelihood function. So in a sense, what's the intuitive meaning of maximum likelihood? Now that we understand that we are trying to maximize the likelihood function, I will write the intuition here. Intuition. Finding or estimating the parameter theta such that it maximizes probability of observing the data. Right? So for example, let's say that, what do I mean by parameter? What do I mean by data? Assume that x1, x2, xn are your data, for example, right? And you know that they are normally distributed. So you would like to find them maximum likelihood for a mu, for a mean of this normal distribution in such a way that it maximizes the probability of observing this data. For example, assume your data is like -1, 0, 1, -0.5, 0.7, -1.2, 1.8, and so on and so forth. Now you're asking, this is the data. This is the data I observe. I ask myself that I'm told that this data is following normal distribution. Then I'm trying to find the maximum likelihood estimation for this data, right? So for the maximum likelihood estimation for the mean of the normal random variable, or the mean of this distribution, normal distribution. So if you, for example, say that maximum likelihood estimation without calculation, we will later on see that it's going to be a sample mean, but without any calculation, you might say that 0 is a good estimator for the mean, is a good maximum likelihood estimator, right? So 0 definitely looks, so let's say one hypothesis is the mu is 0, the other hypothesis is the mu is 10, right? So the question is that which one is maximizing the probability of observing this data? If you look at this data, 0 looks more sense. 0 definitely makes better sense here, right? -1, you have 0, you have 1, -0.5, they're all around 0, right? 10 definitely doesn't make sense. So if you calculate the likelihood function with the mu equal to 10, you will get the lower values than mu equal to 0. This is the idea behind the maximum likelihood. You observe some data, you are going to choose a parameter in such a way that it maximizes the probability of observing this data. Now that we understand what is the maximum likelihood and what do we do, it's a very intuitive process. Now we are going to ask ourselves, what do we do during the maximum likelihood? How do we solve a problem using maximum likelihood? How do we find the maximum likelihood estimate of a parameter? So what I'm going to tell you is usually the setup. Usually, you are given some data, x1, random sample, they call it usually, x2, all the way to xn. They are the random samples, follow a certain distribution, follow some distribution with parameter theta, unknown parameter theta. Okay, now remember, if you have not already watched the last video, please definitely check this out. This is the maximum likelihood is part of frequentist approach. It's frequentist estimation technique. So the parameter is unknown, but it's fixed, right? So theta is fixed, but it's unknown. So the question is that find them. So follow some distribution. So it's better actually so the x1, x2, xn, or let me. I will put this one here. Perhaps I'm gonna add something x1, x2, all the xn, or id random samples, right? Follow them. I will write this on scratch here. Let's follow some distribution with parameter theta. The goal is to find the maximum likelihood, find the ML estimate of theta. So we know x1, x2, xn or IID means independent identical. You might say that what's the point of that? I will explain once I explain the procedure, the step-by-step procedure, then I will tell you how we can take advantage of this assumption. So how do we solve this problem? This is what I'm gonna tell you is general. It can be used for any problem. Step 1, construct the likelihood function. What do I mean by that? L of theta x. When I put x underscore, this means as a vector. This is that is x1, x2 is just a notation, all of x, which is the probability of x given theta. Okay, great. First, construct this. So here we might have some sort of abuse of notation here because it depends on is it discrete or a continuous. we might have a PMF, probability mass function for the discrete, and probability density function for the continuous random variables. So first, we're going to construct this. Step 2, use the property of independence to break the joint density / distribution. That's a step 2. I will explain what that is. Step 3, take a natural log. So in this step, we're going to review what I mean by that, but take logarithm, or in most cases natural log, to convert the product to sum. Step 4, so if you always follow this step-by-step procedure, you never get confused. Step 4, differentiate with respect to theta and set it to 0. So this, the theta, then will be theta ml, the maximum likelihood. Then let's apply to this problem. So what do we need to do? I will use another color here. What do we need to do? We follow the procedure. This is very generic procedure. You can apply to any problem. Any problem that has maximum likelihood, you can apply this. Even if it's not IID, you can use this. You cannot just simplify it further. So construct a likelihood function. You need to construct a likelihood function. L of theta x. I assume it's a continuous. If it's discrete, you use p. It's just some sort of abusable notation. So you're gonna use this one. Let's just use the full x1, x2, all the way to xn, condition on theta. I just wrote the definition of likelihood. All I'm doing is this. Now, what you're going to do is, this is a joint. This is joint density. So now the question is that we write a note here. So you know that according to independence, I'm going to later on release my video on the comprehensive overview of random variable and random processes. I'm going to talk about all these properties of random variables that you need to know, right? But for now, let's review the independence. What independence says when two random variables, if x and y are independent random variable, if they are independent, this means that knowing y doesn't give you any knowledge about x, or doesn't help you about making a decision about x, right? What it means is that p of x given y is equal to p of x, or p of y given x is equal to p of y. These are conditional probability. Hey, I say that if I know y, given I know y, what's the probability of x? Doesn't matter. If you know it y or I don't know y, it doesn't really matter. They're independent. Knowing y doesn't give me any information about that, about x. So now remember the definition of the conditional probability that we have? According to the joint, we define it like this. But then I said that due to independence, p of x given y is equal to p of x. So therefore, p of x and y is equal to p of x times p of y. Long story short, if x1, x2, all of xn are independent, then f of x1, f of x2, this is called joint. Joint property is equal to product of marginal. What is this? What does this one mean? This product sign. Remember, this one is a summation. This one is product. This one. So this one is I from 1 to n, f of xi. This is like this. F of x1, just plug it I, f of x1 times f of x2, all the way to f of xn. That's what it means. It's similar to what we see here. P of xy is equal to P of x times P of y. Okay? So now let's go back here. We are in step 2. We are going to use a property of independence, right? I'm going to take this one. I'm going to copy this one. You all see that I'm going to follow this step. I'm going to copy this one. Perhaps I'm going to write it here, right? I'm going to use a property of independence. This is equal to product I from 1 to n, f of xi, given theta, right? That's all I'm doing. I'm not really doing anything fancy here. All I'm using is a property of independence. I said U2 independence. So wait, if you're not told that they are independent, you can just leave it as it is, as the left-hand side. But usually in all the problems you solve, you're told that they are independent. IID is the simplest assumption we make. Now, in some of the problems you solve, like they follow the Markov assumption, right? Again, for maximum likelihood estimate, you do the same thing. Only difference is that how you break the joint density. Otherwise, the setup is always the same thing as I'm telling you. The setup is always the same. So this is a step 2. Now, in a step 3, okay, so you can go ahead and take a derivative with respect to this. I will call this one as, let me go ahead and name my equations, perhaps. This one, I have it here. Perhaps I can call this one equation 1. I can call this one equation 2, although they are the same. I'm gonna call this one 3, it's the main one. Then this is 4. Now, you can just go ahead and take a derivative with respect to equation 4. You are more than welcome to do this. The challenge is that it's really hard. You have to use a product rule. I can show you with this one. You have to take a derivative of this one with respect to theta. Of course, I wrote it independent of theta, this one, theta. But take a derivative with respect to this, multiply by others. Then take a derivative of the second term with respect to theta, you multiply by the rest, right? It would be really tedious to do that. Otherwise, step 3 is not like absolutely mandatory, but it's for convenience. And since the logarithm is a monotonic function, it doesn't change the estimator. It doesn't change the value of the theta that maximizes the likelihood function. It will change the maximum value, of course. You take a logarithm for one of them, you don't take a logarithm. But we don't care about the maximum value. We care about the theta that maximizes our expression. So let's go ahead and take a natural log here. We take an ln of natural log of L of theta. This is usually known as this log likelihood. You have seen it perhaps a lot. This is called log likelihood, right? This is called log likelihood. This one is gonna be what? It's gonna be summation I1 to n f of xi, right? Why is that? I'm gonna show it here. No, I'm gonna actually show it here actually. I'm gonna write another note here. So I want to take a natural log of this quantity. So what is this quantity? The best thing to do is just write a couple of terms of that. F of x1 given theta, f of x2 given theta, all the way to f of xn given theta. Okay? So what is the log of x times y? What is log of x times y? It's log of x plus log of y. Oh, the same thing here. The same thing is here. Therefore, the natural log of this product is equal to what? Is equal to f of x1 given theta plus f of x2 given theta all limit to f of xn given theta. Well, guess what? This is going to be sigma I from 1 to n f of xn theta. That's all I said here. This is what I said here, right? Now it's a summation. Remember the summation when you want to differentiate respect to parameter theta for the sum of two values, sum of n values. You only care. So the differentiation or integration, they're linear operator, right? So when you take a derivative respect to theta for two terms or n terms, you can just take a derivative with respect to each term and then add them up. You don't need to apply the product rule. It's much, much easier. Let's go back to our color, right? Step 4. Now we do what? Theta ml. We take a derivative with respect to ll. x1 respect to theta is equal to 0. So the argument of theta that maximizes that when you take a derivative is equal to maximum likelihood. Now, you might ask yourself why I use the round, because here is just only one parameter. In general, when you are doing maximum likelihood for two parameters, let's say for normal distribution, you are doing for a mean and variance. Then when you are taking the derivative with respect to the mean, you consider the variance as constant, the sigma square. So you use, in general, you run the rho, which is a partial derivative. But you can, in this problem, if the theta is the only parameter, you are more than welcome to change this rho to a d operator, right? So that's what you do. And in a sense, this is gonna be like this. Let me just, I'm gonna copy this term. I'm gonna copy this one. Great. So now what is this theta ml? What is it? What's the form of this? It's gonna be something like this. G of x1, x2, all the way. It's gonna be a function of a data, right? The theta of ml is gonna be a function of data. I explained in the last video, Bayesian versus frequency estimation. What do I mean by that? See, the theta of ml, this maximum likelihood estimation, is a frequentist approach. I will remind you again, this is a frequentist approach. Frequentists. This means that they only use data to estimate the parameter. Only use data. So the estimator is a function of some constant data plus and multiplied by some constant, right? So this is very important. The estimator is a function of data. I will tell you what this means. I will write it for you. Function of data. Great. So that's an ML, maximum likelihood estimation. That's all. That's all you need to know for ML, right? We know the general way to solve this problem. We know how to use the property of independence. We know exactly what would happen if they are not independent, what would happen if you have a Markov assumption. All that changes is this step 2. This is the main step. The way you break down the joint density. Otherwise, the rest of them is the same. You always take a natural log or take a logarithm. It's just to simplify the product, and you're not losing anything. You're looking to find the theta that maximizes the expression. You don't care about the maximum value, right? Okay. So for example, if theta equal to 4 maximizes our likelihood function, if you take the logarithm from the likelihood function or the log likelihood, again theta equal to 4 maximizes that. So it doesn't change the value of the theta to maximize the log likelihood. Fascinating. Okay, now we understand this. Now let's talk about map. map estimation. This one is very similar to maximum likelihood, but we are not trying to maximize the likelihood function. So likelihood, what we have done for ML, let's first talk about the goal. Goal or objective. What is a goal or objective? In the last video, I talked about the Bayesian approach. Map is a type of Bayes estimator. In future videos, I'm gonna talk about the Bayes estimator, and you will see that how everything actually ties together. Map is a type of Bayes estimator, which means that we are trying to maximize a posterior distribution here. If it's Bayesian, this means that, as I explained before, we use the data plus the, I will write here Bayesian. So data prior to estimate. Use a data plus a prior to estimate our parameter. Great. But what is the goal anyway? The goal is to find or estimate theta. Theta is our parameter, such that it maximizes the posterior distribution. Not likelihood, posterior distribution. Okay, very important. We are not trying to maximize the likelihood. We are trying to maximize the posterior. So what does it remind you? Whenever I say posterior, what should I do? I talk about that. I will definitely recommend you to check out my last video. I will put the link in the description. So again, we need to remind us about Bayes' law. I explained that Bayes' law is a way to relate the posterior and likelihood together. Or in a sense, if you don't want to talk about the posterior and likelihood, is a Bayes' law is a way to relate two conditional probabilities together. Okay, what does it say, the Bayes' law? It says that if you have posterior for parameter theta is equal to likelihood, I'm going to define this term again. So what is this term? This is what we call it posterior. I will tell you what. This is a belief prior. This is the likelihood. And this one, in terms of estimation, we don't care about that because it's independent of theta, but we call it probability of evidence or data. Great. So in Bayesian school of thought, we usually have a prior belief, something that we usually start our problem with a prior. I have some hypothesis about what is the probability of this hypothesis, right? I have two hypotheses. Let's say, for example, in a system, communication system, either one is transmitted or zero. In a likelihood, a maximum likelihood estimation, or in frequencies, you said that, okay, they're equal likelihood. 0 and 1 are transmitted equally. But in Bayesian, you might say that, okay, 0 is transmitted probability 0.7. Because of my expertise or domain knowledge, I am kind of sure that 0 is more probable than 1. So this P of theta is the knowledge that you have about the parameter before you start collecting data or before you start observing data. So I will write it here. Knowledge about parameter before observing data. Great. This is a likelihood. What we did in the maximum likelihood. This is exactly the same, right? P of x given theta. This is probability of observing data given the parameter. We define that. This posterior is the knowledge or belief after observing data. After observing data. Great. So knowledge or belief after observing data. So this is the idea of a Bayesian estimation. I have some belief, some prior about my parameter. I go ahead and collect data, observe some data, then I multiply them together. I construct a posterior, and then I'm gonna try to maximize the posterior because I want to incorporate my domain knowledge, expertise knowledge into problem. Okay, great. Now let's continue. Now here, let's take a look at this. This P of X given theta. Sorry, this use another color first to match this one. This P of theta given X, this posterior. This is proportional to P of X given theta times P of theta, right? See, what is the goal? The goal is to find the theta, the parameter that maximizes the likelihood, that maximizes the posterior. I wrote it here, right? The goal is to maximize the posterior and find the theta. What's that P of X in the denominator? This P of X, this one. This is independent of the parameter, independent of theta. So I will write, no need to write that. No need to write it. Since it does not change the optimal theta. So in terms of optimization problem, finding the best estimator, you don't need to write that. This is good enough. Perhaps the time to name this equation again. The last thing we had was equation 4, I guess. This one I'm gonna make it equation 5 just to double check. Yes, 4, and then we make this one 5, the Bayes law, and this is 6. So from now on, let's focus on the 6. Posterior, proportional to likelihood times prior. Great. Now, I'm gonna tell you the step-by-step method to solve this problem. Very, very similar to maximum likelihood. Very, very similar. Step 1. Step 1. Construct the posterior. Construct the posterior distribution. Or posterior density or distribution. Slash distribution. How? Probability of theta given X using this formula. Forget about the denominator, please. It doesn't change anything. You can write it. It doesn't change anything. You actually carry it, actually. It doesn't really change anything. Step 2, use the property of independence. If it's given in the problem, I would write like this. Use the assumption given in the problem. Like independence and other stuff. Step 3, this is very, very similar. It's just instead of likelihood, you just care about the posterior. Step 3, take a natural log. Take natural log. Or in general, take a logarithm. To convert the multiplication to summation. Step 4, differentiate with respect to theta and set it to 0. So theta of map is equal to, so perhaps here I would call this one the natural log of that is equal to natural log of this. Okay, great. Now, you remember I did this for this problem? I want to do the same thing here. So what is the, I remind you, what's the problem? You have some random samples, x1, x2, all the way xn, that there are IID random samples, that they are distributed, follow the distribution parameter theta. And we are trying to find the maximum posterior probability for the parameter theta. So here, first we are trying to follow the step 1. So first you're going to go ahead and assume some sort of a prior distribution for your parameter. Like we call it P of theta, right? Or we call it F of theta. Depends if it's the density or if it's a discrete or if it's a continuous random variable. If theta, remember, in a Bayesian approach, the parameter, I cannot stress this point enough. But I talk about this one. In a Bayesian approach, the theta is a random variable with unknown distribution. It has a mean, it has a variance, it does everything. It's a random variable. So it has a probability density function, or it has a probability mass function, right? So let's consider that the theta is, for example, is discrete, or theta, let's say all of them is continuous, or we can assume it's discrete. Doesn't really matter. Then I'm gonna perhaps use some sort of abuse of notation to use P and F interchangeably, but all you need to know is that a discrete, they have a PMF, probability mass function, continuous, they have PDF, probability density function. Okay. So go ahead and construct the likelihood, construct the posterior. I'm going to use this notation F of x1, x2. So first I want to write the posterior. Remember, posterior is theta, given x1, x2, all the way to xn. This is the posterior. Posterior density is equal to what? Is equal to, there is no equality, is equal to the proportionality sign. You are more than welcome to write the equality if you want to write the denominator, because they are exactly equal. Is equal to f of x1, x2, all the way to xn, given that theta. Remember, this is likelihood. This is exactly what we did in ML. Times, let's assume that theta is discrete, right? So times P of theta. These two are proportional to each other, right? You can assume that theta also is discrete, continuous with f of theta. Doesn't really matter. It's a prior belief that you have about the parameter. Okay, good. Now you construct them first. I will say step one. This is step one. Once you construct this, the rest of them follows. It's a little bit different from the likelihood. We're gonna go over the mechanics. Step two, use the assumption given in the problem. We know they are IID, independent, identical. So what is the problem we are trying to solve? We write this one, xn. This is equal to this. Again, I write this. Now, well, this one is what we are trying to maximize. We don't touch this. We don't have any, we don't know how to simplify this. But look at the right-hand side. Well, isn't this a likelihood? Isn't this just a likelihood? So all I did is just use a property of likelihood, property of independence on the likelihood. Remember, this is a likelihood. This one is a likelihood. It's similar to the last one. Now in step 3, you take a natural log. You take a log. When I said log, I mean mainly it's natural log. Mathematically it's a log, but it depends on a problem or applications. Usually you're dealing with exponential family, and usually you take a natural log. So you get this log of P of theta plus sigma 1 to n fxi of theta. That's what you do. Okay? And now step 4, perhaps formally step 4 is this. You would like to write this one. Theta map is equal to, when you take integral of this log of, or I will write this, I'll take a derivative, sorry, differential this one. Right. So in a sense, mathematically, if you would like to define this as correct, it's like this: arg max of respect to theta of log of f of theta x1, x2, all the way to xn. If you want to mathematically correctly. write it correctly. So you see, it's very similar to this likelihood. This term is a likelihood. It's again very similar to maximum likelihood, what we have there exactly. Only we have this term extra, right? This is the extra term now. So I want to actually do a formal comparison, tell you what you need to know. I will write here as a note. First, map estimator or theta map is the mode of posterior distribution. What do I mean by mode? So let's say this is the posterior distribution, this is the mode. The value that maximizes the posterior distribution, the value that gives you the highest value of the posterior distribution. This is the mode. Okay, that's the first thing. 2 theta map equal to theta ml if prior is the same for all hypotheses, or P of theta is independent of theta. If this is constant, right? If it's like a uniform distributed, if you have 4 hypotheses, each one the probability is 1/4. It's uniformly distributed, the theta map and theta ml collapse to each other. Number 3. So let's take a look at this Bayes law one more time together. This one is similar likelihood. I write both of them, doesn't matter. So you see that the posterior is proportional to the likelihood times the prior. So it's going to be influenced by both of this quantity. But how much? If you have so much data available, then the value of the posterior is going to be influenced by the likelihood. If you don't have much data available, then this prior is making very important role to estimate your posterior, right? So if amount of data is limited, then f of theta in x is influenced a lot by the choice of prior. The abundance of data, then the posterior and the likelihood will be pretty much converging to each other. The abundance of data. So the choice of prior is not as important as the amount of data is limited. Number 4, in digital communication, especially, or in signal processing, in radar, microwave, in estimation and detection theory, when they talk about the optimal receiver, or optimal estimation, I will write in signal processing. Or even machine learning and communication, machine learning / communication, they actually mean map receiver or map estimation. So map, as we discussed about the map, will collapse to ML if we have a non-informative prior. If the prior is the same across different hypotheses. If the prior is constant with respect to the parameter. then map and ML will collapse each other. For example, I have 4 signals. I have 2, let's say 0 and 1, easily. 2 bits I'm sending, 0 and 1. If the 0 and 1 are both equal likely, then map and ML are the same. You can just apply maximum likelihood. You can apply map, but the P of theta is the same. P of theta equal to 0 equal to P of theta equal to 1, and both of them equal to 0.5. So it doesn't really matter, the choice of the prior. So map and ML estimation are exactly the same. Now, as I said in the past, this is about the map and ML receiver. I'm gonna record a video about the generic Bayes estimator, which you will see that the map estimation or map estimator is a special class of Bayes estimator when the cost function is like on and off cost function or 1-0 loss function. For now, that's it about this video. Please, if you like this video, subscribe to the channel, like and share with anyone you would like. Again, I'm writing an article. I've actually written an article about the essential parameter estimation you need to know in machine learning, signal processing, and communication. The article is available online. I will put a link in the description for this article. It has example. It has everything that I discussed here. It has some simulation to help you understand the map versus ML. I will have a link to this article in the description page. So thank you so much for listening. See you all in the next video.